everyone. I'm really happy to be here for the second time, and for this I'm grateful to Dave Talbot and Susan Sherratt. I feel a lot of personal support on their side. And I'd also like to thank Mark Spann and Michael Goodspeed. It's always a pleasure talking to you guys. And I'd also like to thank all of the people from the EU community in general, all the people present here in this audience and people watching us live or in the recording later. It's just so much fun to be around you guys, exploring our beautiful electric universe. So, but what I'm going to talk about today, now for the title of my talk, you might actually notice it's quite weird, but talking about those cognitive aberrations and other kinds of effects like that, I just noticed that people tend to notice and memorize things that they actually don't like, things that make them mad, things that they consider stupid. So I figured that this is the kind of title that I need. And in your programs, it's even better fits my purpose, I hope. Okay, so, but first I want to make some advertisement of sorts. Tomorrow during lunchtime, I'll be giving another talk in the breakout room, so keep an eye on this one if you want to hear it. It's going to be about atmospheric vortices. But what I'm going to talk about today is, first of all, I'm going to talk about the motivation for my research. Why do I consider cometry research interesting? Then I'm going to briefly review the basics of orbital mechanics so that everyone would understand what the parameters are, what is the thing that I'm talking about. Then I'm going to briefly outline the electric comet idea and propose my own really simplified version of it that actually might lead to some predictions that we might then compare to the population of comets that we do have in the solar system. So I'm not going to talk about any individual comet, but I'm going to talk about kind of the population of comets as a whole. Then I'm going to propose a few points for discussion, just some random thoughts maybe. So to start off, why do I consider cometry research interesting? First of all is because the comets are pretty close to us. They're our neighbors in the solar system. They're not so far away, like some distant galaxies or something. There's an ever-growing field of observational data, so every year some comet, almost every day actually, some comet gets discovered. We get more and more data on the comets that we already know. Then it is possible to perform what is called the in situ studies. For example, in situ means in place, so we can actually go there and study the comet kind of where it is, in its natural habitat, so to speak. So this is the image of the Rosetta probe, of course, the Comet 67P, and well, here you can see this dark spot. It's actually the shadow of the Rosetta probe itself, so it's just there to illustrate that we can go there as close as to see our own shadow on this object, and it's really cool, in my opinion. Then laboratory experiments are theoretically possible, at least in the electric comet model. And not only we can do stuff like SAPPHIRE, probably already does, I'm not sure, but I also would like to propose an idea for a possible experiment which is not a very close one in terms of resources, but it's still theoretically possible. We can take, for example, a near-Earth asteroid that has more or less circular orbit, that is more or less easy to reach, and we can put an engine on it and just decelerate it, thus that its orbit would turn elliptical, and to see if it might initiate a discharge. Well, of course, it's not a thing that we can initiate today, but maybe sometime in the future. And the comets were always considered mysterious bodies, and their behavior is highly non-trivial indeed. And so I think that there's a lot of potential for discovery in this area. So to sum up, I think that it's an excellent area for new research initiatives. So as I've said, I'm going to review the basics of orbital mechanics. First of all, some agreements I'm going to consider the usual orbital motion as it is considered in classical mechanics. So I'm going to consider only like gravitational force. I'm going to use it as a black box pretty much as the Newton did. I'm not going to concern whether it is related to electromagnetism or not. It might be true, might be not, but I'm not going to be questioning those things. I'm also going to consider laws of Newton and Kepler as being true. I'm going to use Keplerian laws, actually. You'll see them later. And I'm also going to use this simplification that the mass of the central body is much bigger than all the other bodies, meaning that the sun does not rotate around the common barycenter with a comet because its mass is enormously big with respect to the mass of the comet. So it's quite a straightforward approximation. So, well, in theoretically, the orbital motion, if you put it simple, it's just a free fall. But if you might imagine, if you just kind of switch on the gravity, you would just fall on the central body, and that's it. But to move in an orbit means to have some sideways velocity, so that as you fall, you actually also get shifted sideways. So, as this picture might suggest, to move in an orbit means to fall free on the central body, but always miss. So you never actually hit the surface of the body. You kind of always go somewhere near it, but never actually fall. So the laws of Kepler, the first law of Kepler is that all the planets move in elliptical orbits with the sun at one of the foci. Here we have F1 is the sun. In just a couple of random orbits, might not be real, but under the Keplerian laws, it could have been true. So the second law is that the line that connects a planet to the sun sweeps out equal areas in equal times. It's actually a direct consequence of the angular momentum conservation. But as you look at those triangles A1 and A2, they are equal in their area if the time intervals are equal. And the consequence of this is that the farther we are out from the sun, the slower we are going, and the closer we are, the faster we are going. So the biggest velocity is achieved at perihelion, which is the closest distance, and the smallest velocity is at aphelion, which is the farthest distance. And the third law is that the square of the period of the orbital period of any planet is proportional to the cube of the semi-major axis of its orbit. So it directly relates the orbital period to the size of the orbit. So the bigger the orbit is, the longer it takes for a body to go around, and vice versa. So already I should make a correction that Kepler considered only periodic orbits, so those are indeed elliptical, but we also might consider non-periodic orbits. They are possible, such as parabola and hyperbola. So as I've said, you need to have certain sideways velocity so as not just to fall on the body, but actually to move in an orbit. And well, you might consider putting like an engine on your body, and if you would accelerate, your orbit would become more and more elliptical, and then as you reach the so-called escape velocity, it turns into parabola, so you would just go away and never return. And if you would increase the velocity even more, your orbit would become hyperbolic. And for an infinite velocity, you would just get a straight line. So this means that you're going so fast that the body cannot even change your orbit even the slightest bit. And it kind of relates to the eccentricity, although I've talked about velocity. So only the elliptical orbits are closed ones, and for them, the eccentricity is less than 1. Here we have an example with 0.5. Eccentricity equal to 1 is parabola, and everything more than 1 is hyperbola. And so parabola is sort of a limit case, sort of a waterline between hyperbolas and ellipses. There's an infinite number of elliptical of kinds of ellipses, infinite number of kinds of hyperbolas, only one parabola in between them. So some of orbital parameters that are used to describe the orbits. A is semi-major axis, this half of the horizontal, in this case horizontal size of this ellipse. B is the semi-minor axis, the vertical one. Then we have C, is the focal length. It's the displacement of the focus, which is the sun in our case, from the center, the geometric center of the ellipse. So you might consider this actually being a definition of eccentricity, although usually it's quite different, but you might consider this one because, as you can see, C is equal to A times E, where E is the eccentricity and A is the semi-major axis, as I've already said. So the bigger the eccentricity is, the bigger this displacement is, the more kind of squeezed the orbit becomes. And so for zero eccentricity, we get obviously zero displacement and just a circular orbit. And then we have other parameters like distance to the apoapsis or periapsis. In our case, it's aphelion and perihelion. We have the dynamical parameters that change. V is the velocity, and theta, angle between the kind of direction to the perihelion and the current position of a body. So those two, velocity and theta, they change along the orbit. And as for the name, true anomaly is just a historical name. It doesn't have any real significance. So just for you to kind of feel those kinds of orbits, I've plotted several ellipses with the same semi-major axis, but different eccentricities. So here we have zero eccentricity. As I've said, it's just a circle. Then as it increases, the orbit gets kind of squeezed while remaining at the same kind of linear size. The horizontal one. Here we have a highly eccentric orbit. Those are just those plotted together. And this point is, of course, the position of the sun with respect to the orbit that you would have at certain eccentricity. So, but those two parameters, for example, perihelion and aphelion distance or semi-major axis and eccentricity, they describe the orbit in its plane. But to describe the orbit in the three dimensions, we also need to know how this plane is oriented. So to do that, we need a few more parameters. In particular, this is the inclination of the orbit, plane of the orbit. So it's just called an inclination. Then the orbit might be rotated around the vertical axis. And it might be determined through this longitude of ascending node parameter. And then the orbit might be rotated in a plane of its own. And it's going to be determined by the argument of periapsis parameter. So we need at least three more parameters to determine the position of the orbit in 3 dimensions. And the orbit itself is static, but the object moves in it, and to determine the position of the object in its orbit, we need one more parameter. It might be time, or it might be the true anomaly, for example, this angle between the current position and the perihelion. So, and it defines the current position of the object completely. So, as I've promised, a sort of a really simplified version. Maybe someone would disagree with how do I perceive this, but it's the way that I propose you to look at it. So the idea is that the source of cometary phenomena is in the interaction of the comet nucleus and later coma and tails, when they are already developed, with electromagnetic field associated with the sun and the solar wind. So the internal composition of the object is secondary. It might play some role, it might not. This isn't actually covered here. So what I'm interested in is to try to derive some sort of quantitative description. So to put it simply, to just write down some equations and to compare what do we acquire from this with real data. So I'm going to be interested in trying to derive a probability density function for comets based on those assumptions that I would propose a little bit later. So the probability density means I'm going to find a function. Well, just to put it shortly, I would have a couple of assumptions. From them, I would derive some function which would tell me how many comets should I have at the orbit with the given eccentricity. And then I would look at how many comets are actually there with such an orbit, moving in those orbits with such an eccentricity. So some fudge factoring might be necessary. We'll see later. So here are my really naive considerations, that the sun is a point positive charge, spherically symmetric, and the probability of an object to undergo a discharge, like a cometary-like discharge, is proportional to the potential difference between the perihelion and aphelion of its orbit. So if the object moves in an orbit of a positive charge, then at perihelion, when it's the closest to the central body, the potential would be the highest. And as it moves to the aphelion, at the farthest point, the potential is the lowest. So this is quite the straightforward idea that maybe this potential difference is what governs the probability of this discharge to going on. And again, I want to reiterate, I'm talking about probability, so it's not a very deterministic thing, but since we have some quantity of comets, we can actually consider this like that, in my opinion. So really, simple formulas, just the electric potential phi is equal to k over r. R is the distance that we already encountered, but k contains pretty much all the constants, all the fudge factoring, everything that we would like maybe to insert later, some nonlinearities, some things like the charge of the sun, the constant of interaction, Debye screening factor, things like that would all go to there, but I wouldn't be interested in this right now. I'm only interested in the dependence on r. So for perihelion and aphelion, I just substitute the r with the respective distances, and I take the difference of those two, and I acquire the formula 4, really nothing complex here. Then I use the known expressions for ellipses, substitute the aphelion and perihelion, taking their dependence on semi-major axis, which determines the size of the orbit, and eccentricity, which determines the shape. So I substitute it to there, and I get the formula 5. So according to my hypothesis, the probability of this discharge, P, is proportional to this delta of potentials, which is K to E over A1 minus E squared. So as you might notice here, we have the semi-major axis appearing, and the kind of physical in the denominator, so the more semi-major axis is, the less the probability. And well, the physical reason for this is because as we move farther away from the sun, the field kind of gets less dense. It's very tightly packed with potential difference and the kind of energy density as we are closer to the sun, and it gets more relaxed as we are farther away. So it's harder to sustain a discharge. And I'm not even going to be interested in this. I'm going to talk only about eccentricities today, so I'm only interested in this part that contains the letters E, to E over 1 minus E squared. And here I've got this graph plotted of this function with respect to E. So you can disregard the numbers at y-axis. It's not actually like a probability. It's, as I've said, it's pretty much arbitrary. I'm only interested in the shape of the curve, the the functional dependence itself, not the absolute height of it. And you might see that as eccentricity is equal to 1, we actually move to infinity, which is quite bad actually, but we would need to introduce probably some fudge factoring in order to normalize our probability to unit value, which is a fairly standard procedure. So we would have to introduce something later here. But anyway, we already have something to work with, and I've compared this to the data on real solar system cometary population, and here is the source of my data. So just a couple of quick facts. We have more than 700,000 asteroids known, more than 3,000 comets. And actually, as I've said, almost every day a new object is getting discovered, so this data is already obsolete. Now, 90% of asteroids have orbits with quite a low eccentricity, less than 0.25. 90% of comets have orbits with eccentricity more than 0.5, so they're quite an eccentric orbits. What's quite important, in my opinion, is that no asteroids have parabolic or hyperbolic orbits. So all the asteroids that we know about actually move in periodic orbits, but all the stuff that kind of, as you can see, 1,800 parabolic and 300 hyperbolic comets. So the majority of comets actually are non-periodic, so they kind of go from somewhere out there and never return. But actually, there's a problem with it. A slight problem is that there is almost 1,000 objects that are considered parabolic comets, when in fact they are not quite. Those are the so-called Kreuz comets. Kreuz is a cross in German. This is the last name of the guy who worked on the theory about them. So they are actually elliptical, but they have a period of about 750 years, but their perihelion is almost equal to the radius of the sun, so they never survive a single orbit. I don't know why are they considered parabolic, but it's just a fact. The community somehow considers them being parabolic, and I'll show you later that they actually kind of spoil the statistics in a pretty major way. But anyway, interesting is that no asteroids are on parabolic or hyperbolic orbits, meaning that all the stuff that goes from somewhere outside the system actually is a comet. It cannot be an asteroid. So in electric comet, it's of course something to be expected, because if something goes from far away, it should experience a discharge anyway. So here's the graph that I've plotted. I'm actually going to show you only the lowest part now, so that we could see actual kind of dynamics, what's going on there, because it's not a very easy thing to analyze with this huge spike at 1. So here's the lowest part blown up. So this is the graph that I've shown in the preview of my talk, but it was probably not the best idea, because this graph is integral, which means it shows the number of comets that has eccentricity of this value and all the ones that were before. So for 0.4, for example, eccentricity, I plot on the y-axis the number of comets that have eccentricities of 0.4 plus all that were before, like 0.1, 0.2, 0.3. So this graph cannot fall. It can only rise or be horizontal at best. It's probably not the best option. And at first what I did was to analyze it. I was interpolating this graph. The first part kind of looks like a, let me show you. This part kind of looks like a parabola. This part kind of looks like a linear function. This part kind of looks like a exponential. So I took a derivative out of those just to get the differential graph. And a parabola, of course, would turn just to a straight line. The straight line would turn into horizontal, and exponential would remain exponential. But then I've decided to work in another way, and I've just plotted the differential graph itself. So I've extracted it from the initial data, and here what I've got. And again, this is only the lowest portion of, so that we could see what's actually going on in here, because at 1 we have a very powerful spike of like 1,500 or even more. So I've only given the lowest part. So you can see certain spikes here and there. There's quite a noticeable spike at 0.7. I'll talk about this a little bit later. It might be important in my opinion. But we don't actually observe, well, we observe a strong growth at 1. But as I've said, I'm not going to be interested in the number of comets, but rather in the probability of an object to be a comet. And it means that I'm going to take a ratio of number of comets to the number of all the small bodies that are out there. So maybe there's just no small bodies at all at certain orbits, right? So I'm going to be interested in this ratio of number of comets divided by number of comets plus number of asteroids to determine, roughly at least, the probability of a randomly chosen object to be a comet. So the more comets there are, the less asteroids, the bigger the probability. I hope this is quite clear. So in order to do that, of course, I need the number of asteroids too. So I looked at the number of asteroids. This is, again, the integral graph. Looks kind of like a charging capacitor, but I don't think there's a physical meaning to this analogy. But here's the differential graph. It shows exactly how many asteroids have orbits with this exact eccentricity. So we can see that the absolute majority have less than 0.3 or something like that. But even for quite a big eccentricities like 0.9, there are some asteroids at such an object, with such orbits. But there aren't many of them. So here, the graph that I've promised you, sort of this ratio. I took, for every given eccentricity, I took the ratio of number of comets divided by number of comets plus number of asteroids. And we can compare this to the data that I've shown you, this my prediction of sorts from my really simplified assumptions. Again, we can see the spike at 0.7. I'm going to talk about this in a minute. And another spike, which is kind of close to 1, this one. It's actually only one data point. It just happens that there are no asteroids at this measure of eccentricity, so it's maybe not that important. But anyway, just as a reminder, this is what I got from my assumptions, and here's the comparison. So, well, in my opinion, looks, well, maybe not very well, but kind of acceptable, maybe. So, as I've promised, this 0.7 thing, I actually think it might be important, I mean, this spike over here, because, well, it's just my intuition, sort of, but 0.7 might be important number because, remembering Steve Crother's talk about numerology from last year, like 0.7 might be, for example, like square root of 2 divided by 2, or it might be square root of 3 minus 1, or it might be the base of natural logarithm e minus 2. So there might be a relatively easy way to reproduce this spike, but I'm not sure. This is just my kind of hypothesis, so to speak. This is pretty much the main picture I wanted to show you today, but now I'm going to show you some more data. Maybe you were wondering what kind of inclinations the cometary orbits have, and I was actually quite surprised when I saw the real data because it looks like this. And so you have, well, first of all, let me explain what is shown here. The length of the spike shows the number of comets. You can see that it is in negatives sometimes, but you should take the length as through Pythagoras' theorem. You would get the number of objects, number of comets, but the angle between the spike and the x-axis determines the inclination. So the horizontal spike there means 0 inclination, and the inclination rises. Then 90 degrees mean polar orbit, and as we move more than 90 degrees, it means the retrograde motion. So the orbits backwards, sort of, with respect to the planets, at least. So you see this insane spike at around 145 degrees, so it's 35 degrees retrograde motion, and it's the mentioned Kreutz comets that I've told you about. So it just so happens that, well, at least the theory states of those Kreutz comets that once there was a very big comet and it fragmented and gave birth to, like, well, we know at least of 1,000 or something like that Kreutz comets. So, and it kind of oversaturated its orbit with comets just out of nowhere. And it's quite a big drawback of my method, of my approach, because as we see, there kind of should have been only one comet, but there actually is almost 1,000. And it's not a very good thing. And we should try and kind of filter out the cases like that. Maybe those other spikes that you can see on to the right, they have a nature similar to that. This is the lowest part, again, blown up, so you could see the more fine structure. And, well, in general, I'd say that it looks more or less kind of homogeneous. There are kind of more populated prograde sector. Maybe the collisions were more frequent in this area, well, due to obvious reasons. And then the retrograde sector is less populated because the objects were destroyed due to frequent interactions with, like, major planets. I don't know, it's an interesting thing to look into in a more detail, probably. But again, I want to see a percentage, so I look also at asteroids. So you can see that the absolute majority of asteroids have prograde orbits, so kind of normal, regular orbits, with relatively low inclination. There are retrograde asteroids, some of them, but you can see them here. They are completely overwhelmed by the prograde ones. So here's the percentage, and as you can see, the prograde sector, I mean the percentage of comets with, at orbits with given inclination. So you can see the prograde prograde sector is really low on comets, relatively speaking. But as we move to retrograde, there's more and more comets being there. So the retrograde sector is dominated by comets. Here's the only graph that shows the semi-major axis dependence. It's quite hard to obtain the data because it's very time-consuming. The semi-major axis is horizontal, goes from 1 to 32 astronomical units. That's all that I could have obtained. And from kind of the vertical one is the eccentricity, so it goes kind of into the plane of picture. And the surface shows the number of comets with those kind of parameters. So we can see a huge asteroid belt spike, some spike nearby, probably to relate it to it. But we also see kind of a hyperbolic fall as we move to bigger semi-major axes. It might be related to what I've shown you because my formula kind of predicts that because the semi-major axis is in the denominator. So as we move farther away, we need more and more eccentricity to sustain the same discharge. We see also two stripes between the orbits of major planets and two kind of dead zones where, again, the orbits of major planets lie. So unfortunately, this is all that we could see here. So just a couple of points for discussion. Now, apophenia means to see patterns where there are actually none. So it's a possibility here. We should also always consider this as a possibility because we might just kind of try to derive patterns where it's kind of, well, either there are none or maybe they are not the way we think they are. Sorry for this. Then we might have possible observational issues and biases. We obviously don't know probably the majority of bodies. We only know the biggest ones, and it's probably the minority in our system. So the whole statistics might be kind of different than from what we know. Then other hypotheses are possible, not even, I'm talking about, for example, the electric comet framework hypotheses. For example, we might look at radial velocity, how fast the object is moving to or from the sun. This is the thing that I actually looked into, and you get similar results, but that's not the topic of my talk now. Even a dirty snowball hypothesis might theoretically reproduce the same results. I haven't looked into it, but it's a possibility that if we are to approach this scientifically, we should look into this too. And well, other kinds of hypotheses are also possible. Internal structure, as I've said, it's a kind of a secondary factor in an electric comet approach, but it might be important. We might like to look into the spectroscopical data. Maybe there are various kinds of discharges changing, like the surface chemistry, influencing this spectroscopical data that we might actually have the real data about. Active asteroids are sort of a kind of an intermediate case between the asteroids and comets, and they are, of course, a very important thing to look into because they are kind of there might be some experimentum crucis here, so to speak, because they are, as I've said, the intermediate case between the asteroids and comets. And actually, what I have an idea that, as I've said, I'm working with probabilities. So, well, let's draw an analogy. For example, we have a piece of radioactive material, and every atom has a certain possibility to decay, certain probability. But over time, more and more atoms get decayed. So maybe the same thing could be observed with comets. Maybe more and more asteroids kind of spark up as time goes on, and maybe in, I don't know how many years, more and more comets would appear just out of some regular asteroids. Well, this is the idea that I had. The density thing, we know from Philae data that the density of 67P's material is almost the same as the density of asteroid material, but it's the high porosity that makes it so light in kind of in a bulk in general. So it's also a thing to look into, especially related to active asteroid thing. We should look into what kind of densities do they have. Maybe actually the mass of the object is changing. Well, it's quite an outrageous idea from the mainstream gravitational kind of approach. But, well, who knows? As I've said, comets are pretty mysterious objects. So, a couple of other quick points. Solar activity, of course, might be a factor. I had another idea that there might be a quantizing of sorts of cometary quantity as we move, I mean, with the solar periods, as the orbital periods go, like 11, 22, 33, etc. Maybe there are some like step-like function. I don't know. I haven't actually looked into this. As I've said, I haven't actually looked into the semi-major axis nor the orbital period. So the orientation of orbit with respect to stars might be important, aphelion distance, time spent in outer solar system. As I've said, there's many things possible here, but to kind of conclude my talk, I think that naive electric considerations are moderately successful to describe the distributions of comets that we do observe. Some additional hypotheses might be required. Data might be corrupted, just as the Kreutz comets demonstrate us. We should always be very careful with our analysis. It's good that we have falsifiability, that we actually have more and more means to actually interact with the object that we're looking into. Orbital parameters, surface composition, various chemistry might be important. It's always a thing to look into. But the bottom line is that, as I've said in the introduction, that the cometary research is interesting and potentially fruitful topic. And I hope I was able to communicate this to you. Thank you.